Good afternoon, everyone, and welcome to our webinar. We are going to start shortly. I'm going to do the house rules and I will hand over, and then I will hand over to our facilitator. I'm going to share my screen and do the house rules for today. There you go. Welcome to our webinar, Demonstration of Treatment Technologies for Direct Reclamation of Wastewater for Potable Use, National Water Reuse Learning Forum. Housekeeping items: request that delegates only make use of the video function when speaking. Remember to look at the camera, not the screen. Mute your mic if you are not speaking. Use the chat to post questions or raise your hand to share ideas and engage in the dialogue. Wait for the facilitator to call on you or unmute your mic. Presentations will be made available after we get the consent from all the speakers. This is how you access the Q&A. At the bottom of your screen, there's that icon participants, and next to it is a Q&A. Request that you post all your questions there. Our panelists will be able to respond to you either live or they will just type in if there's no time. And then the Q&A on the other side next to the green button to share screen. Then you can just post all your questions and just carry on, have the conversation. This is our program. I'll just pause for 2 minutes so that people can have a look at it and take a screen. And I thank you. I will request that panelists, please, can you mute your mic if you're not speaking, and videos, and then to avoid the noise. I will now hand over to our facilitator. There you go, Megan. Yes.
Good afternoon, everyone. Thank you so much for joining us today for the second national forum for our project that is done in collaboration with Mgeni Water and the WRC. I'd like to open today's proceedings by calling upon Dr. Nhlanhla Kayibela, who is our research manager for this project. Thank you, Nhlanhla.
All right, good afternoon, good day, everyone. My name is Nhlanhla Kayibela. Unfortunately, my video is just malfunctioning, but I will try to work on it and switch it on as we proceed. Okay, can you see me now?
Yes, yes, there you go. Just
okay. All right. All right. So, like I was saying, my name is Nhlanhla Kayibela from the Water Research Commission, and I will be doing just a snapshot of some of the projects that we have at the Water Research Commission. Tobile, can you please upload the presentation for me? Tobile?
I'm opening your presentation. Just give me 1 minute. I'm opening.
Okay,
now, sorry.
Thanks.
Okay, I'm sharing the screen now.
Okay.
There you go.
All right. Yes, thank you very much. Yes, yes, I can see. Can you go back to the first slide?
This one.
Okay. Yes. So yes, like I said, that I will just be giving really a snapshot of some of the projects that we have completed and some of the projects that are ongoing at the WRC. So the purpose is not really to go into detail, but to just to give you the information. And then if you would like to request the report, you can go to the WRC website, or you can also contact me, and then I can download the report for you. So my presentation, really, I'll just give an overview of water reuse and recycling. Next slide, please. So I just want to differentiate before we go any further that water reuse and recycling refers to two different activities. It could be at household level, where mostly we're talking about grey water, and also we can also talk about the large scale or the municipal scale water reuse. And today that is where really I will be focusing this presentation on. Next slide, please. So early on, when the National Water Reuse Strategy was released as part of the National Water Resources Strategy 2 document, the WRC commissioned a project where really we looked at some of the recommended actions in the National Water Reuse Strategy to really pick them up so that we can really identify the clear gaps of research that the Water Research Commission has to do. So some of the items that we picked up really was to creating an enabling environment, doing research that's going to support regulation or the development of standards for a regulation of water quality in water reuse, and also to look at how can we strengthen governance and also empower or enable and support implementation, and also to look at the stakeholders and the partners, and also to look at some social aspects and also public participation aspects in water reuse planning. And then also the last part is on the development and testing of technologies for water reuse. I think today's project actually falls within this scope. Next slide, please. So the next couple of slides really are some of the projects that we have done thus far. So there is a project that is available, and it comes together with tools for costing and selecting of water reuse or reclamation technologies. That report is also available for download. Next slide, please. And then another area that we've looked at some of the existing plants, the small scale plants that are existing at present. And then we've looked at some of the institutional aspects, how they were planned, how they came about. And also we went further on to look at the cost and operational aspects of some of these water reuse plants. So this report comes in 3 volumes. So you can see some of the case studies, and as well as best practices and some recommendations on how really we can implement a large-scale water reuse. Next slide, please. So this report is also part of a 3-report volume. So the first volume looks at water quality monitoring, how to establish water quality monitoring programs for water reuse plants. And as part of the program also, there is a section really where there are proposed water quality targets based on others that are already existing, for instance, that are used in Namibia, that are used in Singapore, and any other countries really that have already implemented water reuse specifically for potable reuse purposes. Next slide, please. And then there is also a fair amount of work that has also been done on the social aspects, as I mentioned, to look at some of the factors that influence public perceptions. Next slide, please. And the 3-part, like I said, it's a 3-part volume. So there is also some guidance document, which really gives a framework on how to involve the public or how to engage, and at what stage should the public be engaged when it comes to water reuse planning and education. Next slide, please. And then complementary to this work that has already been done. So recently we've also done a survey to look at what do people, the public, know on water reuse. As you can see from the results, so this report is already available on the website, that less than 30% of the population is familiar with the term potable, which means that there is still a lot that needs to be done really to educate the public, so that to enable them to be able to participate in water reuse conversations, as well as in the planning processes as it is required in some of the municipal framework documents like your IDP and WSDP. Next slide, please. So this information on the survey of public knowledge on water reuse has also assisted in actually drafting a communication strategy on water reuse. So this report, this project has also been completed, but the report is not yet available on the website, but will be available possibly by the end of this year or the first quarter of next year. But this is work that has already been done. So it's something that interests you. Please let me know, then I can try to share with you the report. Next slide, please. So other than just treatment technologies, there's also a fair amount of work that is also ongoing to look at a circular economy model for wastewater treatment, which also includes partly the recovery of water from wastewater, recovery of resources, as well as energy generation. So even in this case, there is a fair amount of work and reports that are available on the website for anyone who might need that information. Next slide, please. So other projects really that might be of interest that are some ongoing is that there's an ongoing project that is led by Mr. Chris Swartz that is looking at the status of de facto water reuse in South Africa, just to establish some baseline studies. And then in terms of water quality, these two projects have already been completed. One is looking at the removal of micropollutants and EDCs during wastewater treatment for reclamation. And also there's also another project that is looking at on the biological side of things, anti-resident bacteria and genes in raw water, and also water that is treated from wastewater for reuse purposes. Next slide, which is really one of my last slides. So for this project today, like I said, that it is also part of the work that we have supported at the Water Research Commission. So initially it was a demonstration of technologies at a pilot scale, which really now has culminated to a bigger scale, the demonstration plant that currently Megan will be talking about today. And in the other picture there, it shows the first National Learning Forum that we had last year at Umgeni Water. So with that, that was my last slide. I think the last one, Tobile, is just information for anyone who needs to download any of the reports that I've spoken about. There is our website, and once you're there, if you go to the Knowledge Hub, and then from there, if you type out any keyword with water reuse in it, then you should be able to get all these reports that I have spoken about. So that is that from my side. Thank you very much, Tobile. And I don't know if there are any other questions. Over to you, Megan.
Thank you so much. I'd like to thank the Water Research Commission for being a knowledge and research enabler and assisting South Africa to become one of the leaders in reuse and reuse knowledge. So now I'd like to move on to Dr. Samuel Getahun, who is our postdoctoral fellow with Umgeni Water from the University of KZN, and he is assisting us with the national, the WRC project that we are undertaking at the moment. Thank you. Over to you, Sam.
Thank you, Megan. All right, welcome everyone, and I'd like to thank the organizers for inviting me to speak here. As introduced, my name is Samuel Getahun. I am a UKZN postdoc at Umgeni Water. Today, I will be sharing with you the demonstration of the water reclamation technologies at Umgeni Water. In this presentation, I will go through the following topics, starting with the background. My connection is not very strong during the presentation. I will turn off the camera for the time being. Can't see the camera here now. So I can continue like this until I have a problem. So I will start with the background. South Africa is one of the countries that suffered from severe drought, which has caused dam levels to reach critical levels. Several municipalities in South Africa has imposed stringent measures to restrict water usage by its consumers. This has prompted water utilities across South Africa to consider alternative sustainable sources for drinking water, including reclamation of wastewater from different sources. So water use is defined as the use of reclaimed water for beneficial purposes, which can be applied to numerous applications. To list some of the benefits of water use, it reduces the demand and stress to freshwater supply, eliminate the need to transport water as it is more focused on using decentralized water supply technology, offers a climate independent water source, a dependable water source, which allows communities to be less dependent on groundwater and surface water sources. Reduce environmental impact by removing hazardous substances that can cause harm to the ecosystem. It has wide applications from non-potable use, for example, agricultural and industrial use. It can also be used for direct potable and indirect potable use. The direct reuse demonstration plant at Umgeni Water has a capacity of 2 million liters per day. And the process contains a conventional and advanced treatment plant. The conventional process, as you can see in the flow sheet, contains coagulation, lamellar clarification, and rapid gravity filtration to remove some colloids and suspensions in the form of logs and things like that. However, the conventional treatment technologies are not sufficient as they don't usually completely degrade the compounds. So hundreds of contaminants of emerging concern are usually detected, currently detected in water sources in different effluents from water treatment facilities. So the advanced treatment option is mandatory to deal with these emerging contaminants. As you can see here, we have two process trains that consist of ultrafiltration, advanced oxidation, and hydrogen peroxide and ozone, granular or biological activated carbon filtration, followed by on-site electrolyte chlorination for disinfection of final water. The system is also, a UV system is also being installed for comparison with the hydrogen peroxide and ozone advanced oxidation process. The ATP, this advanced treatment plant has been designed with treatment flexibility. It is designed in such a way to accommodate these two process trains, as well as to provide an option to receive effluents directly from the Darwin wastewater treatment by passing the conventional plant. So this WRC project, K52807, which is a demonstration of treatment technologies for direct reclamation of wastewater for potable use, has started in 2018, and the WRC project manager, Dr. Kalebela, and it aims to investigate and optimize the process for the removal of microorganisms and emerging contaminants, develop operational and maintenance strategies, assess life cycle costs, develop public acceptance strategies. These are the main aims of the project. To address these research objectives, it has put in place different methodologies, starting with the commissioning and performance testing of the treatment, the demonstration treatment plant, and developing a routine monitoring protocol to monitor TOCs, total coliforms, E. coli, and emerging contaminants, and to do life cycle costing to look at the cost effectiveness of different process trains to maximize the operational flexibility and efficiency of the system, develop operational and maintenance protocol, develop public engagement protocol. All this is to see if the current multi-barrier design is adequate, and to see if the reverse osmosis membranes are required, and which class of emerging contaminants should be routinely monitored. So the output of this process will be very useful for to establish a baseline process data. When we consider implementations, there are other factors besides the process data. There has to be, we have to establish the use of remote monitoring technology and advanced process control strategies, as the process is a decentralized water supply system. And one of the issues, which is currently not in the scope of this project, but very critical for the implementation, is the practical application scenarios, which we face daily in water supply and sanitation services, the issue of vandalism. In association with that, we are considering a study into the methods to deal with the materials of construction and maintenance protocol to address that issue. Public engagement. Mgeni Water has started working on the public engagement by accommodating or by providing access to the public for site visits and on-site public interaction at the treatment area, engaging with the municipal leaders, schools, educational institutions, as well as once the plant is operational, it's planning to give access to the visitors in the public engagement to actually test the water samples. And with that, it has built a visitor center, which is eco-friendly. It's green, and most of the furnitures are wood that reflect the purpose of the reuse, as well as to create a welcoming environment to the public. I'm sure we will hear more interesting discussions from Sarah's presentation later with respect to the public engagement and communication strategies later. So Mgeni Water has several initiatives that support the reuse project. One of them is the new Mgeni Water R&D laboratory that is being constructed at PMB. There's also Wastewater has also hired a postdoctoral fellow to help with the direct potable reuse research and implementation of one full-scale sanitation solution that is focused on circular economy approach. So for this, PRG is part of the Umgeni Chair initiative that at UKZDIN that supports the direct water reuse project. Establishing a co-funding chair in emerging contaminants as part of the South African Research Chair Initiative with the University of Pretoria. Establishing collaborations with Durban Institute of Technology and for wastewater technology. We will hear more about the research output from this team through Dr. Dennis later. Establishing collaboration with University of Birmingham to evaluate new technologies for pharmaceuticals and pesticides removal as well. And finally, there is a key R&D project established with UKZDIN as well in chemistry and physics, School of Chemistry and Physics, and discipline of chemical engineering through Umgeni Water Chair at UKZDIN. Saying that, I would like to invite Dr. Becky Gumbi to give us a highlight on the research work that is focused on emerging contaminants and nanomaterials in the wastewater streams. Dr. Gumbi, you can turn on your mic. And just to introduce Dr. Gumbi is a lecturer at chemistry department. He has been working with his postgraduate students on different topics that are relevant to water reuse. Dr. Gumbi, the mic is yours.
Okay. Thank you. I will switch my video off because I don't have constant supply of the internet. So one of the challenges that faced in reclamation of water is a lack of analytical method for monitoring of emerging contaminant. So in this project, we have students who are developing various analytical methods for detection of pharmaceutical, personal care product, illicit drugs. And these students are funded by Umgeni Water and WRC under roadmap. So what I'm currently showing is a method for detection of metal engineered nanomaterial in water. So to estimate the number of nanoparticles in water, we first synthesize gold nanoparticles. We analyze them with TM to find the diameter and the shape, because the diameter and the shape is needed to determine how many gold atoms that make one nanoparticle. Now, to get the total number of gold atoms in a sample, we use Avogadro's number and the molar concentration of nanoparticles. To get the number of nanoparticles, we divided the total number of gold atom by the number of gold atom per particle. So we developed two models. One was based on molar concentration, and one was based to the mass of gold nanoparticles. One had a polynomial curve and one was linear. So it can be used as a calibration curve, and this method, compared to other advanced methods, would use single ICP MS. This uses a simple ICP OES. But the challenge is faced is isolation of nanoparticles from bulk. In this method, we develop a phase transfer that selectively transfer nanoparticles from aqueous into organic phase. So that's it for this slide. Samuel, you can move to the next. So another challenge that we are facing on reclamation of wastewater is setting the regulations in terms of limit of emerging contaminant in these waters, because there is no set concentration compared to other known contaminants such as heavy metals or PCBs. So we developed another method. Now it's not for metal engineered, but it's for carbonaceous engineered nanomaterial. Also, we tried to develop a simple method which uses HPLC and UV detector. We also confirmed the presence of nanomaterial using TEM, as you can see on that picture. But what we did with this method, we applied in wastewater and river water. What we wanted to find out was the concentration of these fullerenes in these waters. So we believe even in reclaimed water, the concentration of carbonaceous nanomaterial shouldn't be much differ from these waters. So reclaimed water shouldn't be treated as an alien. The range should be similar. So that's why we applied in wastewater and river water as well. We found the concentration in water, and sorry about that. We tested the method in Ngeni River and waste treatment plant in Daville in Pietermaritzburg. That's it. Thank you, Samuel. You can move on.
Thank you, Gumbi.
Yes. I'm finished.
Okay, thank you. So, in general, the progress regarding the progress of the project, due to the COVID-19, the commissioning of the reuse plant has been delayed, but the construction and installation is expected to be completed in August, and full-scale testing is expected to begin in November. The preparation of a draft water safety plan and monitoring program for removal of emerging contaminants from direct potable reuse plant has been prepared. Some part is still to be completed. Identification of hazardous substances, risk assessment plan, and with regard to the current technologies and their effectiveness to remove these contaminants has been projected. Protocols to optimize the water treatment unit process for each of the selected process configuration for the removal of the selected microbial contaminants and CEC has been prepared. On the time frame, as I said, the construction is to be completed in August. In September, we will start with the technology evaluation and configuration evaluation of the reuse plant, and the full-scale testing is going to begin in November. To conclude, with the decreasing water supply in South Africa, it is imperative that new alternative water supplies are implemented. Water use has obviously economic and environmental benefits and provide a sustainable water source. The major public opposition issue from preliminary findings show that it is decreasing over the years, which is a good thing, but there is still a lot of work to do. Water use will only become more relevant in the future with new plans and schemes being introduced every year. This demonstration plant, which is set up in such a way that it has control system with several flexible sampling pointers and multi-barrier systems that will allow trace monitoring protocols, has a big potential and presents an opportunity for establishing a national learning platform for direct potable reuse plant in South Africa. Thank you.
Thank you so much, Sam. We are going to be taking questions at the end towards the panel discussion. So at the moment now, we're going to move on to Mr. Brendan Tiernison from Zutari, who's been assisting the City of Cape Town with their reuse initiatives. So over to you, Brendan.
Thanks, Megan, and thanks to everybody else for having me on this. Megan, I'm just going to be sharing my screen. If you can tell me when I've got that right.
We can see it.
You can. Okay. I'm going to present a view up. Again, thank you everyone. And just then to clarify, the City of Cape Town is in the process of implementing a direct potable reuse scheme, a full-scale one, and they have a demonstration plant in operation at the moment, not producing water into the system, but using it for learning purposes. So we have the wonderful opportunity of being involved in that, supporting the city with project planning, design, and preparation and implementation of quite a detailed public engagement strategy. So in all this, I'd just like to acknowledge them, and then also the colleagues here and other colleagues who are involved with this really exciting industry where we are with water generally. In South Africa and worldwide, the reuse industry is just a very exciting time to be part of that. And this is just one little small part of some amazing work that's being done locally and abroad. So with that, let me take you to just a very high level overview of the Fora New Water Scheme, as it's known, the City of Cape Town's Fora New Water Scheme. And actually, sorry, I should just go back one step. Megan and I had some interactions to see, okay, what with such a big project, what would be worthwhile to present on at this forum? And we eventually agreed on us just sharing some of our journey and using the HASA assessment protocols to guide the design and the implementation of the project, and HASA being hazard analysis and critical control point assessment. So how's that been applied? What's the journey with that in both the actual Fora New Water Scheme, the full-scale plant, and the demonstration plant? So the Fora New Water Scheme itself, if I bring up your school water cycles, and can't resist the opportunity to just acknowledge how growing cities now are at the point where they have to reconsider reaching further and further into surrounding geographies to siphon off more water from natural water resources when there's a water source flowing out under our feet potentially that we could steward better, care for better, and make better use of. And I think that's what all of us are about, trying to do this so that water reuse is not just the next water use option, next cheapest one, but it's actually the right thing to do, the caring thing to do. So zoning in on that water cycle there, the Fora New Water Scheme is intended to take water from the Zandvliet wastewater treatment works. That one's selected because it has a decent capacity, a very low industrial contribution to it, and it's currently under a project for upgrading a significant upgrade going. It's been planned for this for a long time. It includes MBR for part of the treatment process. That water will then go to the Fora Advanced Water Purification Plant. That's the new facility that's being designed. It's nearing the end of design for it. From there, it will augment the supply to the existing Fora water treatment plant, which is the City of Cape Town's biggest water treatment plant. It's about 500 megalitres per day. The flow coming from the advanced purification plant will be in the order of 70 initially, and ultimately going up to 100 megas a day. So it augments at a 100 to 500 maximum, and that blends with the flow coming from the existing Steenbos and Theowaardeskloof dams. From there, it then importantly is able to distribute widely across Cape Town, not to any specific community. So the process train, a very high level view, which I'd love to go into more, but we'll just leave it there. The water source coming from Zandvliet has some tertiary treatment in it, not just normal wastewater treatment. From there, it goes through ozone, biological activated carbon, granular activated carbon, UF, UVAOP, in the Fora water treatment plant and distribution. So we call that a carbon-based train. There's no reverse osmosis in it. And again, that's another story. We'll just leave you with some pictures of the plant in its state of design at the moment, and take you then into the HASA, this HASA journey of ours. So what's the purpose of HASA? Well, it comes from the food industry, and is focused very firstly and foremost on public health, on protecting public health. So there's all sorts of safety things like HAZOP studies and so on that are applicable to designing a treatment plant and other plants, but the HASA is very much about what people will ultimately consume. So firstly, their health. Secondly, it gives a basis for regulation. So we can say, okay, how can we be sure that this plant is trustworthy and regulated against that? In some states and countries, that would be legislated. In our instance in South Africa, as it stands at the moment, it serves as a basis for self-regulation, which is almost an admirable thing to be doing. Then it gives us a basis for knowing how we can trust the technology that we use, how we can trust the operations, and finally a basis to assure the public that they can trust this process. So a little bit more then on the HASA process. It gives us a way to manage the risks to the public health, and the way it does this is giving a holistic and robust methodology from the source water right through the tap. And in fact, from concept design through detailed design, construction, commissioning, and into the operation phases, all through that, a real holistic thing. Some of the key elements of that are, it helps us to understand what are the risks, public health risks, and identify with that the contaminants and hazardous events and so on that can influence them. Then what are the right technologies to deal with that? And from there, we end up with the treatment barriers. Also, how are we sure that these treatment barriers, these technologies are working? And based on that, we can put in place a monitoring system. And then how can we be sure, or how do we respond if a barrier fails? Because things do go wrong. And from that, we develop various operating protocols. So a very, very high level look at all of that, but we need to be able to trust all of this. We need to understand what must be proven before we go live with the system, and what is our responses in all the operational curveballs that could be thrown at us. So importantly, the HASA process included a multidisciplinary team that worked through this together, and the core part of it was a multidisciplinary team being shut up in a workshop for a week. But it continues, the HASA process, as you can see, continues through the life of the project. But just to note that the city's project management elements, both their bulk water and their sanitation representatives, their scientific services who are responsible ultimately for compliance at the end, were involved in this, which is a really good thing. Instead of just being saddled with making sure of compliance at the end of the project, they're involved right up front in the early concept design. Then designers from 3 different consultancies, cross-checking each other, an international peer reviewer who's been involved with reuse projects in Australia and the States. And then in the instance of the actual demonstration plant, the contractor who supplied it and operates it was involved. So just some of the steps that we went through in this journey with the HASA, I'm going to just take you through some of those. So the first 2 is maybe the obvious ones to start with, is to identify the hazards and set the limits for those. What are the human health hazards? And then those are a host of them that you would be quite familiar with. I think maybe what's important to acknowledge, and it influences the design a lot, is to distinguish between the acute risks and the chronic risks. And acute risks are the things that make persons sick immediately. They are public health risks immediately, and others that over a lifetime can be a risk. And it's the viruses and pathogens that are obviously those acute ones. The host of different categories, we've then distinguished between the different various other categories of chronic risks. And all of those are measured and monitored regularly. There's about 250 parameters that are measured in total. About 130 of those are sent overseas because we're still developing local laboratory capacity for those. And if I can just then zero in on those hazards and their limits, how we then must establish what the hazards are and what the limits will be for those. So for the acute risks, we use the log reduction value system that you're probably familiar with, and in our instance, looking across various options around the world, the city has settled on the 12-10-10 standard, which is pretty much the strictest, and implemented in California for 12 LRVs for virus, 10 for Cryptosporidium, 10 for Giardia, and then additionally 10 for bacteria. So on the chronic ones, just giving you a feel for how the limits were set in place for some of the few of them. There's a slide just bringing up a few. For instance, antibiotics, amoxicillin for antibiotics, we've measured it at a maximum up to 15,000 nanograms per liter. In this case, we're using the California State Water Resources Control Board guideline as a maximum limit, and you can see from that what that limit is, and that we need a reduction of 90% for that. So for every single one of those parameters, for all those different categories, these limits have been put in place, and that feeds into this whole HASA process. So the next step then is to design the barriers for every single one of those 250 parameters, and for each category of them to design a barrier that will eliminate or reduce it to the required standard. And we end up with a process train there, which I'll not go into just yet. And the next step will then, with that, once you put those barriers in place, we then go through that whole thing and ask ourselves the question, where are the critical control points? Those points that are most important for controlling the process. So what is a critical control point? A critical control points are points in the treatment process that are specifically designed to reduce or prevent or eliminate a human health hazard, and for which controls and monitors exist to ensure the proper performance of that process. So it's no good just having the process step, you must be able to check it. So if I took an example of a reverse osmosis train, the actual reverse osmosis, the process barrier, is the critical control point. We then need a monitor in place to validate that that barrier is intact, and in that case it could be the conductivity. And we would then have in place a protocol that if the monitor detects the barrier is not intact, then a predetermined control action and standard operator response will be initiated. So in determining these critical control points, we followed this process train or flow chart, asking these questions. Is there a hazard? Do control measures exist? If yes, then is the step required to achieve a log reduction or to reduce another water quality concern? If yes, then it's a critical control point. If no, well, could contamination occur at or increased to an unacceptable level? If no, then not a critical control point. If yes, well, will a subsequent step or action eliminate or reduce the hazard to an unacceptable level? If no, then it must be a critical control point. And alternatively, if yes, then it's not, and stop. So you work through that whole thing in that multidisciplinary panel. There's a lot of argument and debating to get to the point where you're happy with how we are ultimately going to monitor this process train. So the next step then, after identifying those, now do these three almost do together, is to validate each of those treatment barriers, and then to select the monitors for making sure that they're working and to develop those responses. So validating the barriers is basically saying, okay, it's all very well to say I've got ultrafiltration in place to reduce microorganisms, but how well do they have to operate? Does that process have to operate? What treated water quality objectives does it have to meet in order for you to be able to claim the improvement in water quality across that? And that's set in place very robustly, looking at research, the supplier information, full-scale operation and pilot-scale operation. And then the monitors, bearing in mind these are complex parameters that laboratories will take weeks sometimes to get a return time on measuring. You need online monitors that are surrogate monitors for each of those various parameters. And you put all those in place and make sure that that would work together with a response procedure if things go wrong. So just to give you an example there, in the ozone process, we go through those various steps, which are shown in the first few columns, and we ultimately end up in question 7. Is it a CCP? Yes. So for ozone, there we're asking the questions about microorganisms. And yes, it is a CCP. We do need it to reduce the microorganisms. On what basis do we validate it? And in this case, we use the United States Environmental Protection Agency Alternative Disinfection Guidance Manual, and we follow those very carefully. Similarly, for ozone BAC, there were disinfection byproducts and synthetic organic carbons. We put in place those same questions. We end up, yes, it's needed. It is a critical control point. And what are the basis for validation? And that's looking at performance, which meant a lot of study of the performance of similar plants and what they were achieving. And I'll skip over that one. So this you go through for the whole process. It's a lot of robust to and fro and integrating the process. And you end up then with the table that I've got now showing each process step. And in this instance, the acute risks and what are the improvements in water quality across each of those steps in terms of log reduction values. And just highlighting, for instance, the ozone, we were on that. Ozone shows us, okay, we want to ultimately get that 12-10-10 standard, and we are claiming, there's 2 water sources at the wastewater treatment works. We're claiming 4033. I mean 32 for each of those different microorganisms. What was interesting in this one, so for instance, let me just note that we claim 4 for viruses where you could get 5. The reason is if we went for 5, we would need a higher ozone level, and then we are worried about creating another problem, which would be excessive bromate concentration. So this whole process helps us to sense check that that the process is integrated together and working in an optimum fashion. Biologically activated carbon, for instance, there we didn't claim, although it is a filtration process, we didn't claim any credits for removal there in the end, because it would introduce an unnecessary and too strict operation performance protocol to meet a very high turbidity level, which is not actually needed at that stage. We can get it at other ones. So the whole process helps us to sense check the design and make sure it's operable, and that it will be reasonable to operate this plant and achieve all those water quality levels. So I'll just skip that to show how we eventually end up with all of that adding up to meet our targets. And then we end up with everything showing overall where are our critical control points. So we had 2 sources. One source is an MBR and another source is a conventional activated sludge plant. The conventional activated sludge source is further treated to polish it so that it can then blend with the MBR flow. And then from there, it goes on to the advanced activated plant. So the CCPs are the actual source from the MBR and from the conventional activated sludge. Then from a biological nitrate, the third one from a biological nitrate removal filter plant. And from there, the next one would be the ozone contactor, the biological activated carbon, the granular activated carbon, ultrafiltration, and UV AOP. So those are our most important things that we need to know all the time that they are intact. So just to show you what we, very high level, what we end up monitoring at each of these. So at 1 and 2, the critical monitors are turbidity, nitrate, and ammonia. And those are chosen because if ammonia or nitrate go out of spec, you very quickly know something is unhealthy with your activated sludge plant. For CCPs 4 and 5, ozone BAC, there are critical monitors are ozone residual, oxidation reduction potential, the UV254, contact time, times the concentration of the ozone, and total organic carbon. For the ultrafiltration, our critical monitors are turbidity and the membrane integrity test. Okay, so once all that's in place, we then design and follow through the design per that HASA protocol. And that HASA protocol would have established responses for when things go wrong. So those must be designed into the plant. Finally, you construct with that, and then you go into the process of validating those monitors and ultimately operating in accordance with that. So the validating of the monitors is basically saying, what do we need to prove before we put this into operation and allow people to drink the water? And when you go into a plant, this is actually a photo from the Swift facility in Virginia in the States. You would see those critical control points on the SCADA screen telling you the health of your system and how you would respond if anything goes wrong at a glance. That's like the heartbeat. It's like taking your pulse when you go to the doctor. So I think just touching on how the demonstration plant then is going through a process of being validated at the moment. We've gone through one round already, and an extensive study of it was done, reported on, and things were identified that needed further work. And that is now, we're just going through the second round of that currently as we speak. So the city has this 10 megalitre per day demonstration plant. It's not a pilot plant. It's not exactly process representative, but there are many other things to learn, and probably the validation protocols of proving before you put into operation are the most important. So it has in place all those things that came out of the HASA study very similarly. And if I just take an example here, it has a UV AOP process. And if I take, for instance, microorganisms, you read across I've zoomed in on the top load. We know that we need to have a certain dose of UV of above 900 millijoules per centimeter squared. And we've got actions for if it drops below that, a first set of actions, and if it drops even lower, a second set. And similarly, if I just distinguish between that as an acute and then a chronic one, if we're looking at NDMA and 1.4 dioxane, there's different parameters to monitor. In that case, it's the chlorine dose that gets dosed into that. And there's a set of actions that have to happen if that drops or goes off, and a set of responses to a failure that must happen. So those are all in place, and we check those in the validation process. We sample, we put the plant into production. Everything is operating in its sweet spot. We take samples, we send them overseas, we get the results back, and we check all the operation data versus that water quality data, and then compare it all together and then understand if the plant is ready for validation to be confirmed or not. So what comes out of that, if I go back to that UV AOP, it's just some little things. So for instance, here I've zoomed in there for the microorganisms. We are noting, okay, there were some questions about how that UV dosage was recorded throughout that period. And we noticed that the UVT was observed to drop below 90% for 4 periods during that day and wasn't properly flagged yet. So that's a concern. Even though the water quality showed things were okay, that's a concern. And then that goes into further research and makes sure that the plant fixes that problem before that it can be validated. Similarly, for the chronic, there was something that came up with the chronic where the chlorine dropped slightly lower than it should have for periods longer than 15 minutes, and we question, okay, did you respond in accordance with your hazard protocol or not? And then make sure of all of those things. It ends up in the water safety plan, and hopefully at the end we'll have learned a hang of a lot through this whole process about how to get to the point of, it's just one thing to design the plant, but then to say, okay, we are happy that it's operating properly, monitored properly, and can be put into operation. So that's the end of our process. We still got a bit to go, but we're thick in the midst of it, and we welcome any further questions later. Thank you.
Thank you so much, Brendan. Please, everyone, when you registered, there was a survey that we would like you to fill in. So if you could also fill in that survey, there's a link in the program that you had previously. So yes, now I'd like to move on to Mr. Sydney Masha, who's going to go through eThekwini municipalities initiatives. Thank you so much for joining us.
Good afternoon, everyone. Thanks, Megan, for the introduction. My name is Sydney Masha from eThekwini Water and Sanitation. I'll be taking you through the initiatives that we're doing as a municipality in water reuse. We've got quite a number of projects. We've got one active plant at the moment that's supplying industrial wastewater. And the other one is the demonstration plant at our central wastewater treatment works. And then the other one is still under construction. So I'll be taking you through the presentation. Just give me a sec to share the screen. Just need a confirmation. Can everyone see my screen?
Not yet.
Thank you. Okay. There you go. Can everyone see it?
Yes,
we can
thank
see
you.
it now.
Okay, great. Yeah, so I'll be, like I said, I'll be taking through the reuse initiatives that we're doing as a municipality. But before I go through that, I'll be just going through background of eThekwini. So eThekwini has a water demand of about 963 megaliters a day. It tends to vary now and again. Now that we're going into the December period where we have a lot of visitors, that tends to shoot up to 100, more than 1,000 megaliters a day. And then when we experience a dry season, that tends to drop quite significantly. So right now we're averaging about 963. And then from that, we treat just more than 500 megaliters a day of wastewater. So eThekwini is mainly supplied by three main water systems. So that's the Mgeni supply system and the South Coast system and the North system. But for the purposes of this presentation, I'll just be focusing on the main system, which is the Mgeni supply system. So when you look at this graph, you look at what's the existing supply versus the demands. So our planning branch actually did a forecast into the future where we looked at supply versus demand. So when Spring Grove was commissioned in 2014, we were fine for that period. Obviously, we experienced the drought in 2016, 2017 that pushed the demands down a bit. But now that we sort of normalizing a bit, but looking at the dam levels at the moment, we're not too confident at the moment. But nonetheless, we have initiatives as a municipality going forward as a mitigation measure to overcome the shortfall of water supply in the city. So one of those initiatives is water reuse. That might be direct or indirect, and remix, which is a form of reuse technologies. Obviously, we have the Smithfield Dam, but as you all know, that project is a bit delayed at the moment. I think it's been pushed towards 2030. So that puts the city into a great risk going forward if we don't implement these projects as a city. So we also have a water reuse strategy document and a water security of water supply strategy document, where it says eThekwini's water and sanitation supply will be 20% will be made out of water reuse components. So that's going to the future. We need about 200 megaliters of a day of water reuse. So in the past, to overcome the shortfalls, Ngeni also did feasibility studies looking at implementing desalination in the north or the south coast. We also looked at the Loam Komasi system. Obviously, that was a cheaper system to implement, hence the desalination in the south coast system was paused. So that's where we were with Ngeni. And then as a city, we have three main initiatives. So that's the Northern and Kwamashi water reuse plants, the Remix Water project, and the Durban Water Recycling plant in the south. So those are our initiatives. So I'll be taking through each one. So we have a water reuse PPP feasibility study that we're embarking on at the moment. We're still in the feasibility stage of the PPPs because we're following the PPP guideline in terms of pursuing this project. And once we're done with those aspects of it, we'll look at technology selection as well. And then we look at how we can implement this as a PPP model. So this project is based on two plants. So that's at Northern Works and Kwamashi Treatment Works. So this one's at Northern Works. This slide comes from our water reuse strategy document, where we looked at implementing water reuse at a capacity of 50 megaliters a day at both plants. So combined it would be 100 megaliters a day. So we also were approached by industry nearby. One of the biggest there was NCP Alcohols, who were interested in purchasing the effluent from the tertiary plant for their reuse section. So for boilers, anything else in their process so that they can use water reuse plants. And then also in the strategy document, we looked at what we can use as well nearby. So there were golf courses and other industrial players as well. And then at that time when it was considered, we looked at direct water reuse. So that will tie into the northern aqueduct that feeds the northern parts of Durban. Also at Kwamashi Treatment Works, same projects. We looked at implementing 50 megaliters a day, also be feeding northern aqueduct as well, and the nearby golf courses. But in parallel to that, we also implementing a reuse pilot plant at Kwamashi Treatment Works. I think one of the objectives of the pilot is also looking at water reuse and also looking at a new wastewater treatment technology, which is called MABR, which feeds air using the spiral thing that you see on the right, top right. So that feeds air into the wastewater, and then it's more efficient than the current systems that we have in place. We obviously have those surface aerators at most of our treatment works. So this technology was favorable to us because of a lower energy consumption and its ease of use for operations. So it's new to the country, and we just wanted to pilot it as well as we can implement it on our future wastewater treatment works upgrades. And then part of the pilot plant is attaching this wastewater section to RO units and AOP and other tertiary treatment as well for piloting water reuse. So the reason we chose Kwamashi Treatment Works is because of the PPP bigger project. It feeds into that. We can use the results from the pilot plants that will determine the ultimate process of the PPP arrangement. So we also looked at potential stormwater reuse and direct potable reuse at our Mbelo Treatment Works. This is still at very conceptual stage, where at the moment we appointed consultants to look at how feasible it is to take stormwater and reuse it. and also to take some of the effluent that's being treated at Mbele Treatment Works. So that plant will potentially have a capacity of 21 megaliters a day. So there are a number of options there, whether it be indirect or potable or direct effluent reuse. So that's still in the early stages. The other project that we're working on is the Durban Water Recycling Plant. This is based at our Southern Treatment Works. It's actually our first PPP project in the municipality, where we implemented a 47.5 megaliters of a day plant, where the treated water was supplying both Mondi and Sapref. So it was a 20-year concession contract that was obviously signed in the year 2000. The contract is about to expire at the moment, hence we renewing or looking for a new concession partner to take over that plant. So that PPP contract will be coming out soon. So the attractive thing here is it's supplying industrial effluent to industry partners. We also have large wet industries in the area who are interested in taking this treated water for their processes, including Toyota and Engine in the area. So we have bigger offtake partners as well. So it will be a viable project. So that project, the contract will be coming out, should be in the next few months as well, to get a new concession partner. But also in this project, because Mondi was downsizing their plants because of economic issues that they had and business issues as well they had. They were not drawing as much water as they should be. So we also looked at potable reuse as a potential as well. So the feasibility study indicated it was feasible to implement a 10 meg direct potable reuse plant as well. Although most of the effluent that we're receiving for Southern Works is mostly industrial, we have a line that receives wastewater from Chatsworth, which is mainly domestic. So we'll be using that section for that plant. So we'll be looking at implementing an RO unit there for 10 meg, and then supplying to our nearby reservoir as well for direct potable reuse. So that's the option that we have for this upcoming contract. So in the past, on another project, in the past, we looked at implementing desalination as a mitigation measure for the shortfall of supply. But I think, as everyone knows, desalination has a high energy consumption figure. Although at the moment we're sitting at about 3.8, 3.7 kilowatt hour per cubic meter. It's still very costly for us to implement. Hence, this technology came into place. So this is one of our demonstration plants. It's called the Remix Water System. Just to quickly take you through the process, it's basically a combination of reuse and desalination, where the reject from the BWRO units will go into the seawater section. We will dilute the seawater for basically reducing the salt concentrations in the seawater from 30,000 milligrams per liter to basically half. So by doing that, you reducing the osmotic pressure required to take this seawater through the RO. You reduce it from 60 bar to about 30 to 40 bar. So in this project, it's about, say, 36 bar that we're using. So then that will produce the product water. And so the advantages here is the energy consumption is significantly lower than compared to conventional desalination, where maximum power consumption here, it's about 2.6 kilowatt hour per cubic meter. And the other advantage is the brine discharge into the sea. You're basically abstracting and discharging the same salinity amount. so which is about 3.5%. So that's the main advantages of this technology. And so how it came about is, I'm not going to take you through the details, but we did a pre-feasibility study in 2013, and we selected Central Wastewater Treatment Works as a site where we're implementing this demonstration project. So in 2016, that's when we signed the MOU with the Japanese government. So this is how the project is, team is made up of. So we've got NIDO, who's the funding agency of the Japanese government, who is funding this project for us. This project is at no cost to the municipality. So it's a government-to-government partnership that we entered into. So then Hitachi then was appointed as the implementing agent for this technology. And then obviously Oricon and WSP then did the feasibility studies going forward. So this is how the site looks from top level. So the top right section that you're seeing there, that's the entrance of the Durban Harbour. We chose to abstract from the harbour rather than the direct opposite of the treatment works because of the wave action that we were getting. It was more feasible for us and more cost effective for us to construct a 1.5 kilometer pipeline and abstract from the calmer waters of the harbour entrance. CSIR actually tested that water for a period of a year, and we found out that it's mostly clean all the time. I think the concern then were, we've got ships that are passing nearby. What about fuel or oil that would be, contaminating the seawater? But then when they tested and found the results, it was actually negligible, to a point where there's no algae as well, and they eliminated the DEF units from this treatment process. So when you look at, this is Central Wastewater Treatment Works, so it has a capacity of about 135 megalitres a day. We treat mainly effluent from the city, so that's Durban Central, which is largely domestic. So it's about 92% domestic effluent that we are getting. And that's the demonstration plant site. So Central Wastewater Treatment Works only does mainly primary treatments. Then we separate. I think the way it was designed is we have incinerators on site to incinerate the sludge, and then the effluent will go out to the sea. So the other advantages of selecting that site is we have an existing seawater outfall that we can utilize for this project. However, because we only have, we're only doing primary treatment, we're not doing any advanced wastewater treatment, we had to actually implement or design an MBR plant for this remix demonstration project, just to deal with that advanced wastewater treatment. So this is how the plant looks from a 3D model. So on the left, top left, there's the MBR tank, and then on the outside you will see all the tanks of the building. And then in the middle of the building, next to the control room, we also have a visitor center where anyone is welcome to visit the plant and to see how it's running and performing as well. So in terms of timelines, the plant was commissioned in February this year, or late February of this year, and we ran it for 2 to 3 weeks. However, as you all know, we went to a level 5 lockdown because of COVID. Unfortunately, we had to shut down the plant, and we're still in the recommissioning phases of the project. So obviously that severely affected how we are moving forward with this project. So at the moment, most of the plant is back online. It's just the SWRO that we are working on, and that should be fully commissioned in the next, I'll say by January, February next year. And then we'll demonstrate that plant for a period of 12 months. So then if we're confident in the process, then we'll start building reticulation pipelines into the city. where mainly the product water will go into the city center for now. And then once we upgrade the plant in stages, so that'll be from 6.25, which is the current capacity, to 50 megs a day, and ultimately 100 megaliters a day. That will both feed the city center and the southern parts of Durban as well. So that's the ultimate plan for this project. So as a city, as you will see, that we implemented quite a number of reuse plans at the moment. So one of the concerns that came out for our public participation meeting for the Remix project was how safe is this water for us to consume, and it came out in the feasibility studies as well. So what we currently doing is we're doing a risk-based approach for our PPP project, including the Remix as well, where we're looking at testing the effluent that's coming into the treatment works, and then looking at how safe it is for us to consume. So it will be a risk-based approach, screen all the pharmaceuticals and ADCs that are present in the wastewater, and see how we can cost-effectively test those parameters for operations point of view. So that's where we are. We're still in the early stages because of funding issue. I think most of you are aware that we're having a challenge as a municipality in terms of finances because of COVID. So that took an impact of particularly on this process, because we entered into a partnership with CSR, where we looked at doing this testing. However, just hit a brick wall at the moment because of funding issues. But however, we'll endeavor and pursue that process and see how we can implement it in the future. So UKZN also did testing for us via our current collaboration for the DWR plant, where they screened all the effluent that's coming into both lines. That's mainly from Chatsworth for domestic line, and the industrial line that's coming in from the wet industries. And they found out some of the pharmaceuticals present in the water, that's and caffeine as well, that was mostly abundant. But so that's how we're gonna implement it into the other project as well, where we're doing a risk-based approach. So that's how that DWR plan to be handled, and our other project as well. So yeah, I think that's it from my side. Thank you.
Thank you so much, Sydney. We will move on now to look at emerging contaminants in the context of reuse. So I will invite Dr. Isaac Amowa, who received his PhD in health sciences from the Durban University of Technology in 2018, and has been working as a research fellow for the Institute. His research focuses on health-related water microbiology, with specific topics in parasitology, antibiotic resistance, wastewater reuse, microbial health risk assessments, microplastics in the aquatic environment, and recently wastewater-based epidemiology for COVID monitoring. So to you, Isaac.
Hello, everyone. As mentioned, my name is Isaac, or Dennis. So I'll be giving a presentation on emerging contaminants in the context of reuse. So more or less we'll be presenting on some of the key emerging contaminants that should be considered in a reuse scheme. The previous presentations have mentioned a lot of these emerging contaminants. So more or less to put everything into context, why they are important and what we are seeing in terms of emerging contaminants within the South African wastewater environment, where the relevance is important for us if you are considering reuse of the wastewater. So basically, emerging contaminants sometimes are referred to as emerging organic contaminants, depending on the type, or contaminants of emerging concern. And there are varying definitions that have been proposed in the literature. So I just put these two because they sort of bring different aspects of the term emerging contaminants into play. which is important, I feel, for our discussion. The first one is looking at synthetic or naturally occurring chemicals or any microorganisms. Emphasis on the microorganisms, because there are other definitions like the second one that does not talk about microorganisms, however, has the issue of transformation products. So the second from Geisen looked at in terms of a natural or synthetic chemical or their transformation products. Now, the reason these two different definitions are important is that if you're looking at the emerging contaminants, most often there's the neglect of microorganisms, and then also there's a neglect of the derivatives or the products of these emerging contaminants, like your antibiotics, for instance. I mean, most of you may not release the antibiotic in the parent compound structure. You may have derivatives of it as a result of metabolism within your within the human system or within animal systems, for instance. So this is the reason why I felt it is important to highlight these two different categories of emerging contaminants that should be important if we are looking at wastewater reuse. So looking at it in broad perspective in terms of the different classes of emerging contaminants that have been reported, we have the pharmaceuticals, we have the prescription drugs, drugs of abuse that have been detected in wastewater and of course are important in your reuse schemes. Like most of the other previous presentations that are interested in emerging contaminants have already spoken about. We have the personal care products. I mean, there are different kinds of personal care products that lead to the release of emerging contaminants into our wastewater environment. Then we have the microorganisms, and in there, most often we're talking about the pathogens, but then also we can talk about the antibiotic-resistant pathogens or antibiotic-resistant genes as something that is of importance, which is becoming an emerging issue. Then, of course, there are new pathogens, as we are all aware. Of course, due to COVID, we having this as a virtual learning forum instead of in person, and that is one of the emerging pathogens that are coming out, which are relevant for us to begin to look at how do we account for this when we are designing a water reuse system. Then, of course, we know about the industrial chemicals that find their way into our wastewater systems, which may find its way into reclaimed water. Then there was mention of disinfection byproducts. These are also very important because if you look at wastewater treatment systems largely within South Africa, there's a lot of chlorination taking place as your tertiary treatment option. That might lead to the formation of disinfection byproducts, and these are becoming contaminants of emerging concern. Then, of course, there are the plastics. We have the macroplastics, which is what we can all see. But then you have the micro and nanoplastics, which are becoming a major issue because of the size component. So these are different classes of emerging contaminants that should, be of importance to us if you're looking at the wastewater reuse systems. And the ones I've highlighted are these ones that I may give a bit of detail on it because it relates to some of the research work that has been going on within the institute that I'm currently in and being, led by different colleagues in the institute. So I took this from a publication that some of my colleagues worked on, Dr. Khalid and Lucky, looking at emerging contaminants within the South African context. So this is what they were able to find in terms of what has been reported in relation to the different emerging contaminants in our wastewater systems in South Africa. And there are different classes or categories of these emerging contaminants that they were able to find in the literature. They have the endocrine disrupting compounds like a triclosan, which is very predominant from what we are seeing. And then we have the pallets, which are also of great importance and within the emerging contaminants context. Then you have your medications, either being pain medications or antiretrovirals or antibiotics that, or even anti-inflammatory drugs that have been reported in our wastewater treatment systems in the effluent. So it is important in looking at these different classes of emerging contaminants if we are considering reuse of the treated wastewater, because these are of health implications to the populations that may consume the wastewater or any exposure pattern. So this is in relation to what has been reported in terms of the removal efficiency of these different kinds of emerging contaminants in our wastewater treatment systems in South Africa. In as much as we have some of these treatment plants being able to remove completely most of, or some of the emerging contaminants, there are reports of, let's say, zero removal, and then reports of, vary removal in terms of the different treatment systems. And this is, I think, critical if you are looking at reuse systems, because then instead of having your reclamation plant basically designing that, we should look at where your source water, in this case, your treated wastewater is coming from, in terms of how efficient are the treatment plants in removing these emerging contaminants, and what could be done maybe to improve the removal efficiency, and then also what could be looked at in terms of your reclamation plant. I mean, the technologies that have been presented have largely taken these things into consideration. So it is, I mean, reassuring to, be part of these discussions as well, to see what is being done, that we are not neglecting these. But then, of course, these are looking at the chemical emerging contaminants, but then as this presentation goes on, I'll present other sort of emerging contaminants that I feel we should begin to consider in our reuse schemes. So this is sort of an example of a WRC report that I read in relation to different endocrine disrupting compounds that have been detected in wastewater treatment plants in South Africa in relation to their removal efficiencies. And so if you look at the effluent quality in terms of the daily mass load that is going out of these treatment plants, it is of a major concern, because, I mean, there's de facto wastewater reuse, I mean, happening anyway in many areas within our country. So if it is not going to a reclamation plant, that means that whoever is reusing this wastewater that is coming out of our treatment plants may be exposed to these sort of endocrine disrupting compounds in wastewater. So to contribute to the area of emerging contaminants in wastewater and how that is impacting on reuse, there's quite a few research projects going on in the Institute. I'll just give one or two that are relevant for this discussion. The first one is the fit and removal of emerging contaminants during chlorination of drinking water. Now, and the important aspect of this is because, as mentioned earlier, there are disinfection byproducts that are formed during these chlorination processes. And so these disinfection byproducts are becoming contaminants of emerging concern on their own. So the first objective is to determine the occurrence of selected emerging contaminants in source water and effluents of selected wastewater treatment plants, and to look at the removal efficiency within these different plant units, and to consider that in relation to the operational parameters, that is looking at chlorine concentration, contact time, pH, and all these different parameters that may affect the chlorination process, and that may have a role to play in the disinfection byproduct formation processes in total. And to look at it in terms of contribution towards the removal, there's a strong research focus within the Institute on algal biotechnology, and there are quite a number of reports that have sort of alluded to the use of algae as a bioremediation approach for removal of key emerging contaminants. So we looked at it in terms of antiretroviral drugs that are commonly found in our wastewater treatment systems. And we do know the antiretroviral drugs in our wastewater treatment systems are a major issue within South Africa. So the idea is to see how well can the algae that we can find in our wastewater treatment systems, or the algae that we have found actually in our wastewater treatment systems, how well they are in removing these antiretroviral drugs. And so that we can be able to consider the use of maybe algal biotechnology as an option to remove these contaminants in your wastewater before it even goes to your reclamation plant or before it goes for any reuse purposes. Okay, so if we move beyond the chemicals and we look at the plastics as an emerging contaminants, the main issue is that, I mean, most of us do know about the impact of plastics on the terrestrial life forms or aquatic life forms, but the issue is that microplastics may be what is well known, but if you look at the smaller size, the micro and nanoplastics, these are of great importance, because if you are looking at your treatment systems, I will show some few results that we found so far in terms of what we have been able to pick in our wastewater treatment systems, even in the effluent, in terms of these micro and nanoplastics. And that is becoming a major issue, and not just because the plastics themselves may affect life forms, but then what is attached to the plastics. So because in the wastewater systems, you would have, it's a complex environment. You have different kinds of emerging contaminants like heavy metals, antibiotics, and all these other contaminants that may get absorbed onto your microplastics. Now, in addition to that, you have microbial colonization, biofilm formation, which has been reported to enhance antibiotic resistance development. So then again, these microplastics may act as Trojan horses for the transmission or dissemination of emerging contaminants and even pathogenic microorganisms in your environment. And that is becoming a key issue, because if you have nanoplastics, which are formed as a result of a breakdown of the larger plastics, then this may go through your treatment processes, carrying all these different kinds of contaminants, and they may be exposed to the populations thereafter. And this is just in sort of why it is important for us to consider the micro and nanoplastics in terms of their uptake within by living organisms, because then if you have your chemicals attached to it, your plastic is not the only thing you should be concerned about, but what else the plastic is carrying. So if you look at within the plastic or microplastic scenario in wastewater within South Africa, there's a bit of lack of information on the wastewater side of it. There's quite a lot of studies that have been done on the freshwater and marine environments, but generally in relation to wastewater treatment and removal of microplastics, this I took from a global study that reported about 95–99% removal may occur. However, I mean, you will still have about, if you're looking at about 65 million microplastic particles released per day, if you're looking at it in terms of the amounts that they were able to find in literature from other areas globally. So looking at our treatment plants in South Africa will be very important for us, because most of us in this forum will be aware that, I mean, our plant efficiency varies. There are some plants doing very well and the others that still have some room for improvement. So the release of these microplastics into the environment is a key thing that we should be looking at. And the work done on the freshwater side in terms of microplastics, again, a WRC report that I saw, the data that they were able to pick up to about 56 particles per liter in freshwater, which is a great concern, because then if you're looking at the amount of water that you will use for different activities, then the exposure to these microplastics will be high. And then, of course, the exposure to whatever else comes with the microplastics is of concern. And so within South Africa, if we look beyond the wastewater side, there's quite, as mentioned earlier, a lot of work. This is just a few examples within the marine environment and within sediments, where they've been reporting over 1,000 to 3,000 microplastic particles per liter or per meter square of sediments. So this shows that, you know, this microplastic is a major issue within our environment. And so for that reason, as we look at other emerging contaminants like your antibiotics, like your endocrine disruptors, we should begin to look at microplastics in that regard as well. Now, so because of that, there's a project, again, funded through the WRC as part of the JPI water projects, which we are doing with collaboration from France, Norway, and then Cyprus. The idea is to look at micro and nanoplastics as carriers for the spread of antibiotic resistance in the aquatic environment. So to be able to achieve that, we structured in a way first to characterize the type of microplastics that we find in our different wastewater systems in South Africa, looking specifically within Durban, and then to evaluate the removal of this microplastic through the wastewater treatment process, to be able to see which of the processes are actually efficient in removing these plastics that are of concern, and to look at the factors that influence adsorption of different contaminants like your DNA, which we are interested in the antibiotic resistant genes, and also microorganisms to these microplastics. And finally, to look at the tertiary treatment options available and how that may impact on the microplastic material itself, the DNA adsorb onto the microplastic, and then the microorganisms adsorb onto the microplastic. The idea is to give that kind of data on how efficient our plants are working, what our plastics are going out, and what those plastics are carrying as we move along. So this is just a preliminary data that we've got from the treatment plants in Durban. And this is part of our progress report that has been submitted to WRC before. We found microfibers, we found microfragments, we found microbeads, microfilms, and this just to give a picture in the sense that the microplastics in our wastewater are coming from different sources and they are coming from different parent materials. So then it becomes important for us, because then when you're able to have an idea in terms of the source, where it is coming from, you can also be able to have, interventions either based on education or any other kind of intervention that may reduce the impact of these on the wastewater treatment systems. But then again, it helps us understand what is happening in our treatment works before it goes out in the effluent, and then maybe when this effluent is being reused, what impact it may have on the populations. So we went further to look at the microbial association with these plastics. So these are just some of the same images that we got to actually show that there is microorganisms attached to these microplastics. But then the question is, what microorganisms are attached? Are these of concern to us in terms of the public health? So that is a study, that's a part of the study we're still working on, trying to then have an idea what type of microplastics are attached and what it tells us as we move forward. So beyond the plastics, beyond the chemicals already mentioned, I did mention the issue about the microbial pathogens or microbial contaminants that are of emerging concern. We have the emerging pathogens and then re-emerging pathogens. Now, the emerging pathogens, of course, those are new, that may not have been infectious to humans, but because of change in lifestyle or whatever, they are becoming infectious. And the re-emerging is, there were pathogens before, their incidence reduced and is increasing again. And that is as a result, most of the time, due to antibiotic resistance development. This is some of the data we picked up from different publications, different works within South Africa, reporting on different pathogens which are emerging and also other indicator organisms. The reason I put a first table is because we should begin to look at ways to measure these emerging pathogens beyond the indicator organisms like the E. coli, because it has been shown not to be very representative of these emerging pathogens that we should be paying attention to. So that's just to highlight that when we're looking at water reuse, let's go beyond the indicator organisms to look at specific pathogens that should be of interest to us. And then, of course, talking about the re-emerging pathogens, that is important because of antibiotic resistance. And that's something that we all know about. In fact, South Africa is one of the countries that consumes a lot of antibiotics globally. I think among the top 5 or top 3 in the world. So antibiotic resistance is widespread. And for that reason, the pathogens that we are getting may be of great concern if you are looking at the reuse in your wastewater. Some have shown 100% resistance to most classes of antibiotics that are currently used, and that should be major concern for designing a reuse scheme where we should be measuring these re-emerging pathogens and resistance as well. Now, the question that, SARS-CoV-2 in the wastewater reuse perspective, what should we be concerned? Should we pay attention to it? Now, there's been a lot of reports on detection of this virus in wastewater, and that is based on it's used in developing your wastewater-based epidemiology for monitoring COVID infections. So of course, you have the infection, you have the virus being shared in feces, going into your wastewater treatment systems that may go out to your effluent, depending on whether you have a treatment going on or not. But there are different treatment processes that could actually remove that. Now, this is just an example of what we have found in part of the work we are doing in the Institute, contributing towards the wastewater-based epidemiology for COVID monitoring. The load of the viral genome that we found in our wastewater treatment systems within both Pietermaritzburg and Durban. And we found between 2.8 to about 3 log copies of the SARS-CoV-2 in the untreated wastewater. Now, the issue is that, will this go through to your treatment process and be effluent, for which reason it should be concerned when you are looking at reuse of the wastewater? One, from literature, what we've seen is that we can get about 3 log removal of the enteric viruses. So it may not be a major issue. That's if you're looking at activated sludge processes. And then there's data to show that about 26% of the coronaviruses will be adsorbed to the solids in your wastewater. And therefore, when you go through anaerobic digestion, you get almost close to 6 log reduction of your enteric viruses or the coronaviruses during that process. Now, membrane treatment processes will reduce almost close to 3 log. So what I already showed in the influent, the maximum we are getting is about 3.2 log in your untreated. So through these treatment processes, it's most likely that you remove most of the viruses, and whatever will be remaining may be the nucleic material, but not a viable virus. So in fact, in a lot of studies have tried to look at the effluent of different treatment processes to see if we can find this virus in there. And there are different reports, varying reports. Others have found nothing, especially when you have tertiary treatment. Those that have found a bit of viral load is having secondary treatment processes. And so that is something that we should be looking at if you're talking about SARS-CoV-2 within the wastewater reuse perspective, where there is a potential. So I need to just raise this, that the fact that you are detecting the virus in your untreated wastewater does not mean it is infectious. It could just be the RNA. And the RNA in this case may not be what should be of concern. It is a viral particle that is still viable. There are different studies have been trying to look at that. None have been successful yet in culturing this virus to show that it's still viable in the treated wastewater, for which reason it should be of a great concern in reuse schemes. However, it is important to have this in mind because SARS-CoV-2 may be what we are dealing with today. Tomorrow, there may be a different kind of virus coming up. So when you are developing your reuse schemes, then these are some of the things to consider. That your emerging contaminants should not only be the chemicals, the plastics, and the endocrine disrupting compounds, but the microbial side. Microbial side also should look at these smaller particles that could actually go through your treatment processes. So finally, to end it, so what do we do in terms of emerging contaminants in your reuse schemes? The guidelines, we've been looking at the guidelines that have been reported in terms of South Africa. What has been presented about 10 log removal value, that is what most of it, like what was presented. But then we should be considering these different classes of contaminants that should be added to your guideline values to ensure that you are not only considering a particular class of emerging contaminants, but you have a good representation. Then you look at the methodologies for detection and quantification, these analytical methods. So already the second part of the presentation, after Dr. Samuel presented some of the work that they are doing in developing analytical methods. That is also something that is ongoing within the Institute to develop capacity in detecting these emerging contaminants, which are of concern to us. And then, of course, the technologies that are used for the wastewater treatment could also be improved so that your treated wastewater would have less amount of these contaminants so that your reclamation plant does not have to deal with a higher load going forward. So that is the end of my presentation. Thank you very much. And the contacts are there in case there's need for further discussions on this. Thank you.
Thank you, Dr. Moa. Just for the sake of time now, we will go straight away to Dr. Jacob Fix, who's going to be discussing measuring emerging contaminants in wastewater. He's got his PhD from the University of Umeå in Sweden and has been a professor for a long while. He's also had several ongoing research projects in close collaboration with the Pollution Research Group at the University of KwaZulu-Natal. Over to you.
Thank you. Thank you for presentation, Megan. Do you see my screen right now, or do you see my slide presentation screen?
It's the slide screen.
Ah, good, good.
Yeah, sorry, so it's not the correct one.
It's not the correct one. All right, so I have them in different. I will stop share and then I will share the other one instead. So is it correct one now?
Yes, thank you.
Thank you. My name is Jerker Fick, and I'm an associate professor in chemistry and not IT technology, as you might know by now. I work at the University of Umeå in northern Sweden, and I've been having an ongoing collaboration with a researcher at UKZN and DUT for quite some time now. So what I will be presenting are measurements of emerging contaminants in wastewater in eThekwini municipality. I started out I'm initially a pharmacist, so I will focus a lot of my research is focused on pharmaceuticals, but I acknowledge what Dr. Amoa said previously, that emerging contaminants is not just pharmaceuticals, it's a lot of chemicals. And I agree that also, of course, microorganisms should be included. However, most of this talk will be focused on pharmaceuticals. But that's a bit of a bias based on my previous background. So when it comes to pharmaceuticals, we know that there are 3,000 to 6,000 pharmaceuticals on the global market. No one can really decide how many they are because there are different definitions in different countries. We also know that we use them grams per day, and that they're not toxic. I mean, they are meant for human consumption, and they have side effects, and they have ecological side effects, but they're not toxic in the sense of many other chemicals. And it's a big business. So one of our first difficulties when it comes to measuring environmental contaminants in wastewater is the selection. As I said, there are 3,000 to 6,000 pharmaceuticals to choose from. So which are the most relevant, and which one would you like to include in your analysis? So I usually start with the usage. So if it's not used in your region, you can't find it in the water. So you need to sort of know a bit about which chemicals are used. But you also need to know something about the fate. Many pharmaceuticals, as also Dr. Amoa mentioned, are metabolized in the human body. Some are not, but some are more or less removed. And you could have metabolites, but you can also have just carbon and carbon dioxide and other things. So you need to know the fate both in the human body, but also in the sewage treatment system, and perhaps even the pipes leading to the sewage treatment system, because they could be removed quite quickly. So a chemical that could be reused quite a lot, like the beta-lactams, an antibiotic, they are actually removed even before they enter the wastewater treatment works. Then also you need to think about relevancy. Which endpoints, what would you like, what do you consider to be relevant? Antimicrobial resistance, of course, is a high concern here in my country. So measuring antibiotics is really relevant. Measuring pharmaceuticals that you know are non-toxic, some pharmaceuticals that you know are non-toxic and that you don't really have a good endpoint in exposed biota, that perhaps is less relevant. So you need to think about that as well. If you're going to do study on different removal techniques, you can also start thinking about having a diverse set of chemical properties. Then you can use this as a proxy. You can make a chemical map and say that chemicals that are similar to these ones would probably be removed as well. You can also think of proxies in the sense that if you know the usage, you can measure one or two of these antibiotics or these pharmaceuticals, and if you have an increase, you probably have an increase of all the others as well. We talked a bit about the general public, and of course, societal interest is of great concern. That's the question someone has to answer at the municipality. So you need to think about what are the common opinion, what does the local papers write about? We had a huge incident in Sweden with polyfluorinated compounds, and the scientists hadn't really taken interest in that previously, but the big societal interest, and they asked a lot of questions that we couldn't answer, meant that we had to do our homework, learn how to measure them, and then go measuring them. And of course, me being an analytical chemist, there are analytical issues as well. When you select things you would like to measure, some pharmaceuticals or some chemicals are more difficult to measure than others. You need to have commercial standards. You need to get proper ionization. You need to have a decent limit of quantification. So even though it's relevant, it's highly used, it's very interesting, sometimes you just can't measure it. And that's because we aren't good enough chemists, but we're getting better. It's also a sort of a time issue or a cost benefit issue. If it's of high interest, of course, high importance, more time spent would perhaps solve these analytical issues. Sometimes. As I said, I've had long ongoing collaboration with UKZN and DUT. So I will present some results from the Ithaquini municipality. So we've been looking at wastewater from 3 wastewater treatment works, and also a decentralized wastewater treatment work, the DVATS facility in Nulan Mashu. We also looked a bit on the recipient. So we have included also this 4 river water concentrations. So I will show that later in the presentation. So in our first study, we also choose to look at antiretrovirals because that's a group of drugs that is not that well studied. There's been some studies in Kenya and some other studies in South Africa, but we don't really know that much about the fate of these chemicals in a water treatment system. They're highly used, especially in the Ithaquini region. And we included 13 antiretroviral drugs, basically because the regime changed a bit. And I think these samples were taken before the new regime as well. So which drugs are used at the moment will, of course, decide the influence levels, the levels in the influence. So this is a study we did, and we have we included 2 wastewater treatment plants and this decentralized wastewater treatment plants as well. one thing you should know is that this decentralized wastewater treatment plant receives its wastewater from 84 households, meaning that individuals could impact the levels quite dramatically, because you're working against statistics. I mean, if you have 100,000 people connected to a sewage treatment plant, if 1 or 2 gets off the medication or go away from the region for a week or 2, that won't influence the general value. But in a DWAT system, you can see things like that. So individuals can have a large impact. But what I would like to show is that I would like to highlight some of it's a busy figure and a lot of numbers, but I would like to highlight 2 things. First of all, that there are 2 antiretroviral drugs that are present in quite high levels of influence. So abacavir and sidovudin, but are removed quite well, really well actually. So they're not that much present in the effluent. But no, of course these, and then you have these 4 pharmaceuticals that are present both in the high levels in influent and also high levels in the effluent. And these are really high levels. I haven't seen many publications that show these kind of levels, high microgram levels in the treated effluent. The problem we have with these antiretrovirals are that we don't really know the ecological impact of them. So we don't really know what they will do once they enter the environment. Basically, I have one issue with the human safety for reuse, for consumption, but also you have if you're going to reuse it in agriculture, for example, you have the plant uptake and other things as well. So not much is known about the ecotoxicity of antiretrovirals. But as I said, the removal is quite high for most of them. What you see here is actually negative removal. So there are higher levels in the effluent than in the influent, which is common in sense. Some pharmaceuticals are excreted from the human body as conjugates. They have a sugar moiety or something attached to it to make it more water soluble to get out of the human body quicker. And these conjugates, we don't measure them with this method, so they are sort of not detected in the influent, and then they are deconjugated within the sewage wastewater treatment process, and we measure them afterwards. And this has been shown for lopinavir, for example, which is one of the antiretroviral drugs we included in the study. Apparently, it could also be a sampling artifact. We try to accommodate sort of the same water flow through the retention time of the wastewater works, and sometimes we fail. And there is a clear diurnal sort of there's a different levels in the wastewater depending on the time of day as well. So it could be a sampling artifact as well, but it's something we see sometimes, and we usually see it for these pharmaceuticals that have this conjugation metabolism going on. The other group that we have been looking at are antibiotics, and the driving force behind this is, of course, antimicrobial resistance, antimicrobial resistance development. So we studied 13 antibiotics in 4 wastewater treatment works. I'm running out of time, so I will focus on the most important things. I would like to highlight these 3 that we included: metronidazole, ciprofloxacin, and albendazole, and especially ciprofloxacin and albendazole, which are present in really high concentrations in the incoming influent, but not very high in effluent. High enough, I would say, for ciprofloxacin. I will talk more about that later. But as you see, ciprofloxacin is present in microgram levels in treated effluent. Ciprofloxacin is a drug antibiotic used to treat pneumonia, and albendazole is anti-worm medication. And the levels in the influent also it directly reflects the usage in that particular part of the city or sort of in the catchment. So it also reflects how much domestic versus industrial waste goes into the sewage treatment plant. So you can see that it differs quite a lot between the different wastewater treatment plants. But the removal rate is more or less the same. That's actually quite unusual because sewage treatment plants are usually quite individual, that they have a very, so you can see the removal rate is similar for most antibiotics. You have erythromycin, which also have a negative removal, which have this deconjugation going. But otherwise, you see the removal rates, there are some individual variations. Some sewage treatment plants have a higher and lower for some pharmaceuticals. And this is a operating thing. This is seen in all sewage treatment. Wastewater treatment works globally. Some seems to have a design that increased the degradation of some or removal of some chemicals and not others. So it's a very common thing. So it's a really good initiative to look further into this, sort of look at what kind of retention times, what kind of processes are present in the ones that have the highest removal. As I said, we also looked at the receiving river. So we took a water sample 100 meters downstream the discharge of the effluent, which is perhaps a bit more interested, not in reuse context, but perhaps ecological ecotoxicology context. But you can clearly see that the recipient river is highly impacted by the discharge. And more importantly, perhaps at this site where you have actually quite high ciprofloxacin levels. So this level of 710 nanograms per liter is actually high enough it's above the threshold level where you predict it to be promoting microbial resistance, which is of course of high concern, because if you have microbes exposed to ciprofloxacin and they get resistant towards that, these microbes could then transfer the resistant genes to pathogens. So the next person that get pneumonia can't be treated with ciprofloxacin. You can also see at some cases, I think it's this one for albendazole, for example, that the receiving river is actually have a higher concentration of some of the pharmaceuticals than the effluent, which could be a temporal event, that it could be the discharge could have been at high concentration previously, or at that this recipient, this river, is impacted by other anthropogenic activities. So more wastewater treatment works upstreams or diffuse sources. We also looked at, so our last campaign, we included more pharmaceuticals. We actually included 71 pharmaceuticals selected because they were used in South Africa. They were sort of, we knew the fate of some of them at least, or we would like to know the fate of others. And we looked at this is in the DWATS facility only. So this is the study 3 consecutive days. And you can see that there are quite high, we included quite a lot of different classes of pharmaceuticals, and also pesticides and herbicides as well. We didn't find any herbicides. So these are the 24 pharmaceuticals that we could detect out of this 71 that were included in the method. And I would like to highlight some of these. When it comes to diclofenac and the ciprofloxacin, these are above the threshold levels. The diclofenac level is above the environmental quality standard level that is currently discussed in the European Union. Ciprofloxacin is above the threshold level for antimicrobial resistant development. Fluconazole is, according to one source, is actually also above this a threshold level. When it comes to these 2 antiretrovirals that we were detecting in the effluent in the highest concentrations, lamivudine and nevirapine, it was quite interesting to see that darunavir had this more or less same concentration as in our first study, but lamivudine, which seemed to be quite well removed, have a high removal efficiency in the previous study, did not have that in this study. So there are factors that are affecting the removal rate that we are not aware of right now. And I would like, I see my time is out and I will stop, but one of the problems when you try to highlight pharmaceuticals like this or for chemical or environmental concern is you don't really know what protocol to use, so what to compare with. With that, I would just like to thank my co-authors and colleagues and the helpful staff at the Pollution Research Group at University of KwaZulu-Natal, and thank you for listening. Sorry.
Thank you so much, Jaco. It's really, really interesting, and I hate to stop people, but yeah, just for time's sake. We'll move straight on now because all reuse projects depend on public buy-in. And next we have Dr. Sarah Slabbert, who is the Managing Director of BHI 32. And she is going to take us through a presentation called Paving the Way for Water Reuse Literacy in South Africa. Thank you so much.
Thank you, Megan, and thanks for everyone. It's a great privilege to be here this afternoon. My presentation has been pre-recorded, so Tabile, will you play it for us?
Okay, I'll load it now.
Okay, thank you. Yeah, one of the disadvantages of a pre-recorded is that you can't adapt it to what the very interesting things that the other speakers were saying, but there would still be opportunity for questions. Tabile, you'll have to share your audio as well. Tabile, you'll have to share your audio, otherwise we won't be able to hear.
Sorry about that. Let me redo it
No
again.
problem. These slides. According to the Water and Sanitation Master Plan, South Africa is planning to increase the contribution of water reuse to up to 20% of the country's water supply mix. Water reuse includes a range of applications, of which direct potable reuse, that dark red arrow, is just one. Water reuse is not without risk, as the Department of Water and Sanitation has pointed out on several occasions. Public acceptance is often mentioned in water reuse discourse as one of the barriers to the successful implementation of water reuse. Lack of understanding of the water cycle and treatment technology is cited in the literature to correlate with negative perceptions on water reuse, and thus a major barrier to the implementation, particularly that of direct potable reuse. Unfortunately, South Africans' knowledge of water reuse is insufficient for an informed public discourse. A Water Research Commission baseline study that was done last year tested basic knowledge of water reuse and related aspects. The study found that large percentages of South Africans are not familiar with basic terminology of water reuse: grey water, potable water, black water, reclaimed water. More than 50% of South Africans do not know that water reuse is part of the natural water cycle. And on average, South Africans scored 12 out of 20 on a knowledge index of water reuse and related aspects. The communication strategy for water reuse that was finalized this year aims to address this lack of public knowledge. The first consultations on the strategy started in 2017, and right until the final workshop in July this year, the strategy grew from intensive consultation with a range of stakeholders. The focus of this strategy is on educating South Africans to become water reuse literate. This would lay the foundation of public knowledge and understanding of water reuse in South Africa. On this foundation, implementing organizations can base public communication campaigns for specific projects. The baseline study showed all demographic groups should be targeted, but messaging is more effective when it is tailored to a specific target audience. And also, multiple related messages through different channels have more impact than a single message delivered through one channel. So how does one deal with all of this? For these reasons, the strategy follows a multi-layered and long-term approach, targeting individuals in their many roles as consumers, as learners, as leaders, as influencers. Targeting consumers at different levels in their interaction with their municipality, in their homes, at a personal level. Targeting business consumers. Targeting learners in different learning stages of their lives, in basic education, in higher education, in professional education, in counselor induction programs. For each of these roles and levels, the strategy maps out a network of organizations working together. At the final strategy workshop, it was hugely encouraging to hear of initiatives from these organizations taking up the challenge to promote water reuse literacy amongst the South African public. DBSA setting up a water reuse program office, which will include support to municipalities to educate their consumers. DBSA supporting the establishment of a central hub of vetted educational resources that would be available to everyone, whether an individual, a municipality, a water-intensive business, or an education institution. Umgeni Water setting up a national learning platform and center. National stakeholder sessions to slowly sensitize people to issues and strategies. Fundisa for Change as a model to include water reuse in teacher training. The Department and the Water Research Commission entering a partnership to target learners in the next phase of the 2020 Vision for Water and Sanitation Education Program. Visa putting up its hand to fast-track public knowledge by targeting influencers and decision makers. And metros like the City of Cape Town leading the way with effective messaging strategies to educate the public and nudge behavior. To conclude, I want to share with you a few thoughts about the discourse on water reuse communication, which came up in the course of the development of the strategy. The first is, what type or types of water reuse do we want the public to accept? Not all types of water reuse will be equally acceptable to the public. The baseline study showed that South Africans across all demographic groups would support water reuse in a severe drought situation, including direct potable reuse. However, their support for other types of reuse is higher than their support for potable reuse. I believe, therefore, that direct potable reuse should be the end point of public education, not the starting point. Secondly, why should the South African public accept water reuse? Must the public accept that municipalities that are barely able or not able to manage their normal wastewater treatment to green drop standards can actually treat wastewater to SANS 241 standards? Would you? Trust in municipalities is a national crisis. Without trust in the implementing municipality, public acceptance of water reuse for drinking purposes is a pipe dream. Thirdly, how do we want the South African public to accept water reuse? I believe we must be careful to call on the public to accept the product of a water reuse project uncritically. It's the public's right to question, to be wary, to want to understand the risks of water reuse. That's the purpose of having a water reuse literate public. Lastly, I would like to put a challenge to all of us. I'd like to call on VISA's Water Reuse Division to organize a national workshop on grey water communication. In our work on the strategy, we found many pamphlets, booklets, posters on grey water use, but they don't all use the same definition of grey water. They have different views on safe grey water use. The COVID-19 pandemic brought new questions about safe grey water use. For example, is it safe for families without running water in their homes to share a hand washing bowl? Or could they be spreading the disease? What's a safe way to dispose of grey water from hand washing if you do not have a drain? Grey water reuse is something that we all can relate to. For the millions of South Africans without a tap inside their homes or a drain, the disposal of grey water is a daily reality. Let's get that communication right and consistent as a quick win to establish a water reuse literate public. I thank you.
Thank you so much, Dr. Slevitt. We're now going to go into a discussion period. So if you've had any questions that you want to ask any of the panelists, now is the time. You can put it in the Q&A session or equally put up your hand. I am going to paste the link to the questionnaire in the chat. So please, if you could fill out the questionnaire. I'd just like to start off the discussion, calling on Brendan. If you could just tell us a little bit about the objectives of the demonstration plant in Cape Town, and then also if you could just give us feedback in terms of lessons learned and just a little bit on the public participation. Thank you.
Okay, Megan, thanks. Are those, Megan, just checking, are those arising from questions that people have had?
No, we're just waiting for the questions to come on at the moment.
Okay. I'm just going to call something up while it'll just help me with that. Just give me a sec. I just had a slide on why that demonstration plant.
We can't see anything at the moment.
Yeah, it'll come up now. Okie dokes. Is it coming up now?
Yes.
Got it. Okay. So maybe I should just briefly explain this. The reason there is a demonstration plant is a little interesting. It was implemented during the drought crisis by the city. The wastewater treatment works that it sources water from, Zandvliet, is operated by a concessionaire. And under that crisis, they went to the concessionaire, who also does other supplier plants and so on, and negotiated with them to provide this facility as part of their if the system is about to run dry initiative. So it was a temporary thing. It was never meant to be permanent, and it was only to be used for water supply in absolute emergency. But once before the plant was even commissioned, it rained, and the city had to then say, okay, do we cancel all these plans, or do we allow them to go ahead and complete it and get some other value out of it? And they chose the latter. And there has been a lot of value gained out of it. And here are some of the things. So firstly, it's not a pilot plant. It was constructed based on the inventory of equipment that supplier had available at the time. And they largely designed it with some guidance from the city, with us supporting them, especially on these validation protocols and HASA protocols and so on. So it's not a carbon-based system. It's a membrane-based system. It has reverse osmosis and process train, but it's much smaller, so the brine from that is not as problematic. So what does it do? It gives the city experience and expertise in meeting these high-quality international water standards. So the standards that this plant operates to, and that the intended foreign water scheme operates to, are far and away above what SANS 241 deals with. I know that SANS 241 has a list of parameters, and then it basically says that, okay, and anything else that could be a threat to human health must be dealt with. But we actually need to know what those are and study those, understand them, identify them, and put limits in place for them, like the previous presenters have been doing. And there's all this research going into it all the time. So this gives them that exposure. Then it gives technical training and testing in operating technologies that are not normal to them. So whether they're advanced or not, I think we could say they're advanced in that they're not the normal conventional run-of-the-mill things that people use, but worldwide they are becoming pretty standard. They're not untested. Then it helps them in the developing of protocols, both for design, then for commissioning, and then for proving before it goes into operation. And this is where it's really been helpful. So if the city can do this when they're dealing with a little plant, or relatively, and not a full-scale monstrosity with a contractor who's waiting for payment and so on, a much more forgiving scenario to learn on. Then it helps establish local laboratory capacity. So all these parameters that we need to measure, there hasn't been a huge driver for it in South Africa. It's growing with the efforts of Mgeni, eThekwini, others have done things, the universities, and now it's been interesting to see how that is driving local laboratories to establish accredited, ISO accredited capacity for these advanced parameters. Then it's developed and demonstrated the city's capacity. So this is feeding into the outreach, the public outreach and education strategy. We have a short little video on it, which if there's time at the end, I could even show to you that they've prepared. It's fairly hot off the press. Then I guess I've already touched on the stakeholder engagement. Then it helps in establishing partnerships for the future. So a lot of those partnerships are even within the city itself. So a big metro city before had wastewater that did its thing, water that did its thing, catchment management that did its thing, compliance monitoring that did its thing. And they did cooperate, but a reuse plant forces a new level of working together for a common outcome at the end. And it's helped establish those. For instance, we've established within the city a water quality focus group, which has different representatives from that keep an eye on everything to do with this plant and check all the validation results and go through that together and vet it. So there's a multidisciplinary view on that. Then yeah, that's it. Those are the key things.
Thank you so much. We have a question for Nonhlanhla. It's from Khalid Ghani. He was asking, was there any psychological framework? Oh, the question has just gone away. When looking at, I think it was looking at the public education.
Okay. Hi, Megan. I saw the question and I just responded to Khalid to ask which survey is he referring to, because I mean, in my presentation, I went through a couple of projects which potentially had surveys. So if the one that is referring to is the one for the public survey on knowledge on water reuse, then Sarah can answer that one. I wouldn't really want to answer on her behalf. But for the rest of the other studies, yes, we did have to formulate some sort of a framework for formulating the survey. So if I refer to one of the studies where we looked at some of the social factors that influence public opinions and acceptance of water use. So that was really informed by, first of all, doing a literature survey, and then also just having informant interviews also with some of the case studies that were investigated in the study.
Thank you. Dr. Slabert, do you want to also come in there just regarding that question, and before we move on quickly?
Yeah, I'm not sure if the question was directed at me, but yes, the study that we did, the big challenge was to answer the question, before we test what the public knows, what is it that we want the public to know about water reuse and related aspects? And that was a consultative process to define a number of fields, knowledge fields, that people working in the water reuse field felt that it was necessary for the public to know, also supported by literature and research elsewhere in the world. Does that answer your question?
Yes, thank you so much. The next question was by Percy Setole. It's for Sydney. You mentioned that the COVID-19 affected the program for Remix. Are you still on track for February 2021?
Thanks, Megan. Yes, we're still on track for February 2021. The level 5 lockdown that I mentioned earlier forced us to shut down the plant for since March until end of July. End of July, that's when the team was allowed back on site. So since then, they tried to recommission the plant. Obviously, it's a long process. It doesn't restart that quickly. Unfortunately, we had logistic issues because we had to reseed the MBR tank with sludge from our existing treatment works, which is quite far from where the site is. Because, as mentioned, Central Works doesn't do advanced wastewater treatment, it only does primary treatment. So we had to source that seeding sludge somewhere else. So When we started that commissioning for the MBR in end of July, transporting the sludge, that took a month, and then once it was reseeded, once the MLSS levels were at an appropriate stage, that took another month for us to balance that. Right now, the plant is 80% commissioned. The only section that we're dealing with at the moment is the SWRO section for the seawater line. So that's where we are. We're just pigging the seawater line and trying to remove the contaminants that are in place, and then we'll start decommissioning those pump station and the actual plant itself. So we're still on track. At the moment, there are no major delays. We should be able to start in February 2021 officially. Like I said, it's 80% complete, but we will hopefully by mid-December, the plant will be recommissioned and ready for the festive season to, like for the leaf side, everything is, normalized and running at a minimal. And then once we back in January, that's when, we'll make sure everything's running correctly, and we'll start officially in February. And we'll operate for a period of 12 months. Thank you.
Thank you so much. I think this is a question for both Brendan and Sydney. It's very controversial in South Africa about reused water and who will be receiving it. Leslie's asked us who is receiving the treated water, and also about sludge disposal. Because we know that we're having a big problem with disposing of sludge at the moment, is with both water and wastewater sludge. So Sydney, if you can start, and then we'll move on to Brendan.
Okay, thank you. In terms of the pilot plant, the product water from the plant is now going for any consumption, whether it's for industrial or for potable reuse. All the potable water is discharged into the outfall. The reason we're doing that is the technology is still new to the country, and once we confident in the quality of the product water, that's when we will start putting the reticulations, supplying into the reticulation system. So at the moment, it's still a demonstration. It's not for consumption at the moment, because it's still a research, or like a research plant at the moment. So right now, we're just proving the technology, make sure it's ideal and perfect for us to implement officially. In terms of sludge disposal at the plant, unfortunately, at the moment, it's going to the sea outfall. As Megan has mentioned, we have extreme challenges as a municipality in terms of how do we handle the sludge. So there's logistics issues that we're facing at the moment. So, and the way the plant Central Works is designed, the plant itself had an incinerator back then. So that's where we are at the moment. So the sea outfall that I'm referring to is a Central Wastewater Treatment Works. That's the one near the Durban Harbour. Thanks.
Brendan?
Okay, Leslie, that's a good question. Similarly to how Sydney discussed his one, the demonstration plant for the city is not being used for potable water, or not at the moment. It may be possibly connected in later, just for a short time, just for the experience. But the important thing is the Fora New Water Scheme, and part of the reason why that one is chosen is because it augments the largest water treatment plant in Cape Town, and then the plan is to link that across to the Blackheath water treatment plant, which is the next biggest one, which integrates those two systems and allows the city to distribute that water broadly across the city, so that when you're doing this, it can never be to a select community. It has to be very, very broad. So that's like a non-compromise part of the project. Then on the sludge, so you almost flick a switch about what I'm really passionate about with a number of things with all of this. But the Full Renewable Scheme uses a carbon-based system as opposed to a reverse osmosis-based system, which is an incredible process. But what it will do, of course, is it will block the contaminants and concentrate them up in a brine. And that brine then needs to be returned to some receiving environment. So you haven't effectively removed them from the environment. They go back to the environment, whether it's to the river or to the marine environment. And that's a problem, especially when you're dealing with a big plant. And it was part of the reason why we went for a carbon-based system, which instead of concentrating and returning the contaminants, rather by and large destroys and removes them, and uses biological processes to break them down to much simpler organic compounds, and ultimately even destroy. So it has a net positive. That whole load is removed. It doesn't go to the rivers or to the marine thing. All these parameters we're talking about, all these parameters of concern and all that sort of thing, we rather destroy them, don't go. So it's a very special thing, I think. The sludge, look, the sludge generated from backwashing of filters, you could call it sludge. It's really water treatment residuals. It's a biological assimilated organic. The bacteria have digested it and it's accumulated into cell mass. So the plan for that is that it gets returned. It's a very small quantity because it has a low microbial cell yield, and it gets returned to the wastewater treatment works, goes in, gets enmeshed with the activated sludge and removed with that, processed with that. And the city has a next phase of work to be done at the wastewater treatment works, where they will be implementing an enhanced anaerobic digestion and hydrolysis, sludge hydrolysis process, which will optimize both the reduction of the mass of that down to inert organic material, and also optimize the combined heat and power that can be gained from all of that. So that whole thing, when that's eventually all done, will be quite a special maximum resource recovery and so on. I hope that answers it briefly.
Sorry, there's just a quick follow-up in terms of the carbon. How are you disposing of the carbon?
So the activated carbon is granular activated carbon. So it's not a compound that's dosed into the water and removed continually. It's beds of carbon. So the biological section, it's basically a filter bed that the biology grows on, and it stays in there in the bed. That's how it is. It goes from that into a granular activated carbon adsorption step, which is similar. It looks exactly the same if you were to go there, and that process, because it's absorptive as opposed to biological, the micro and meso and picopores in the activated carbon will eventually become saturated with the contaminants that it removes, and will need to be reactivated. So then you remove all of that, which would happen between once and twice a year for each bed, depending on how much the plant is used. And it then gets steamed, basically, which burns off those contaminants, and then the carbon gets reused. There is some attrition, and you need to top that up, but anyway, that's that process.
Thanks so much. And then from Khalid, he asked why a 10 megaliter per day plant instead of 1 or 2 megs with regards to the sorry, you just jumped and gave me a fright.
I realized I hadn't put my video on, sorry.
Yeah, with regards to the demonstration plant, because he says with the capital cost, why wouldn't you just go smaller for demonstration?
It's an obvious question, so thank you for asking it. And it's because of the history that plant was put in to make us, well, small in terms of our overall city, but a measurable and helpful contribution to surviving the day zero drought. So that plant was put in for that 10 megs. It would have been distributed. You know, you could come and collect your drum of water from that and other sustainable sources. And when the drought broke, the plant was basically repurposed from a production plant for day zero crisis to a demonstration plant. And so it was never downsized. It couldn't be, the ball was already rolling.
Thank you. We've got a question for Yaka. Parent compounds, for example, antibiotics, are further broken down in wastewater treatments. Have you tested for the broken down byproducts?
Yes, we do that sometimes. It's part of the selection process. What's good about most antibiotics and most pharmaceuticals are that they metabolize, the breakdown products are less good at what they are doing compared to the parent compounds. There are some exceptions to this, but mostly that's the case. Basically, pharmaceuticals are designed to fit a certain drug target, a receptor or a protein. And any changes you do to that, any chemical changes you do to that structure will just make it worse at acting as a pharmaceutical. So most pharmaceuticals are the most interesting ones are usually the parent compounds, and there are some metabolites with a therapeutic effect as well. It's the best example is the beta-lactam, the penicillins and the beta-lactams that are broken down on the beta-lactam ring. So the part that is active towards killing microbes is the part that also breaks down initially. So you lose all antibiotic activity. There's no metabolite of any penicillin or beta-lactam antibiotic that has any antibiotic properties anymore. So it's if you want to play it safe, go for the parent compounds. They are designed to have an effect, and you know they will have. There are some metabolites that can actually have more effect than the parent compounds, very few. And most metabolites are boring in the sense that they have a 10th or 100th of the activity of the original parent compound. Then there are these exceptions to the rules where some byproducts, there's a byproduct from diclofenac, for example, that more or less turns into a PCB molecule. So there are some interesting exceptions as well. But if you stick with the parent compounds, you stick with the main mode of action, and that's usually what you're interested in. Did that answer the question?
Yes, I think so. I have a question for the whole panel in terms of the South African context. Where do we see reuse in the future, considering that we have rural areas that are really far away from our big metros? As we can see, eThekwini and City of Cape Town are implementing reuse in towns. So in KZN, we have large areas that are quite isolated. How do we overcome this in terms of reuse? I'd like to start with Sam, and then if anyone else wants to come in after.
Thank you, Megan. For me, so far, is like different aspects of the reuse has been covered, but we still lack a regulation that or a guiding document that will enable us to have a guideline basically from the Department of Water and Sanitation for water reuse. That may include the aspects on water quality variables of concern, quantification of risks associated with that, and at acceptable risk levels, and monitoring requirements in terms of frequency and location of sampling are critical. That part of the reuse has not been properly covered. In my opinion, that is one of the things that we need to address to go forward with the reuse projects. Thank you.
Thank you, Sam. Sierra, in terms of public perception, you asked some very hard questions with regards to trust. How do you propose that our municipalities can create a framework to move forward and create this trust so that people would start reusing water?
I think the various aspects to that, Megan. The first of all would be another hard thing to do, maybe, is to get your house in order. Municipalities need to prove to their consumers that they can treat wastewater to the required standards. And then they need to talk to their consumers, not only when they're implementing a water reuse project, but continuously, and ask themselves, are we accessible to our consumers? Can they pick up a phone and get actually answers? And do we continuously educate them on what reuse entails, all different aspects of it? How well informed are our consumers? Those are two aspects that I think would be very important for the success of a water reuse project.
Thank you so much. Just one last question for Dr. Amoa before we close. Just in terms of looking at CECs, there's so many contaminants that we're looking at. In terms of the public, how do we create a balance in looking at what's actually bad for us, what's good to know in terms of research, and then how do we stop from scaring people into not wanting to even participate in reuse and reclamation?
I think the contaminants that we should be focusing on should be based on what we have within our region and what is of concern to us. Because let's say, for instance, like the work that is being done on antiretrovirals, it may not be a major concern for different areas. But within South Africa, it may be a big issue in terms of antiretrovirals in our wastewater treatment systems and going through to our reclamation plants. So that should be one. And then also in terms of, let's say, antibiotic resistance, because again, South Africa antibiotic consumption is quite high. So it should be based on what we know of the situation. So I do see that most of the times they do sort of a preliminary studies to find out what are the different emerging contaminants within the wastewater, from which you then target on what you could focus on. The other aspect is that if we have, that will also lead into the guidelines, you know, in terms of what should be the guidelines for us in South Africa, and what should be the concentrations that we should consider as acceptable or, I mean, of low risk. So then again, that means that we need to have a risk assessment of the different contaminants that we have in our systems, and then find out what is the concentration that is of relevance in terms of the health implications, so that we have a system that, yes, we can look at international standards, we can copy what others are doing, but it is more custom to our situation. So it should be based on what we want and what we are looking at. Again, one thing that I wanted to highlight is that in terms of the reuse, I mean, most of the discussions have been potable reuse. That's where the large issues are. But the largest consumption of water in South Africa is actually agriculture. So if you look at treating the water for agriculture purposes, then you will reduce the demand for water in the agricultural setting. And even in terms of the quality, the treatment quality that you need for agriculture is maybe much lower than potable reuse. So then it also reduces the cost involved in the whole reuse, process. So in that case also, then the contaminants that you should look at may be lesser than when you're looking at potable reuse. So that would be, I think, my response to your question in that regard.
Thank you so much, Dr. Moa. So now, thank you. We just want to close. So we're looking at reuse projects, and the aim of our reuse projects is to be able to give information to decision makers so that they can create policies and strategies going forward, so that by 2030 we are not in the situation where we require 17% more water in South Africa than we actually have accessible now. Thank you so much for joining us, and goodbye.
Thanks, Megan.
Thanks, Megan.
Thanks, Megan.
Thank you, Megan.
Thanks very much, Megan.
Thank you, Megan.
Bye, everyone.